Okay. Um, all right. So what we're going to start with today. So last semester, working primarily with means-based analyses, like group-based comparisons, right? Like, is this group? Do we have evidence of population differences in this group versus that group based on some of the data that we've run? What we're going to transition in the second semester here is working with more continuous variables as predictors, right? And what we're going to do today is start with talking about the general linear model. This is just kind of the big overarching framework that covers a lot of different types of analyses, including the ones that we did last semester. We're going to talk about some basic assumptions, different variations on the generalized linear model. This is important in sort of trying to help show of hands, like who might sort of have anxiety about like, hey, I'm going to have to do a thesis or a dissertation at some point and trying to figure out what analyses I use. Is that sort of people worry about that thing sometimes? Yeah. If you understand GLM, if you understand level of measurement, what your IVs are, what your DVs are, you got it all figured out. Like if you can sort of specify those things, all of a sudden the analyses that you should run start to reduce down. It starts to become very easy to decide how do I go through and sort of what analyses do I pick. So we're going to talk about variations. We're going to get into correlations, talk about different tests that we can do with correlations, different stuff that we can do with correlation coefficients that can be quite useful. And then we're going to finish up with different types of correlations and how they relate to things that we've already kind of talked about and know about. Okay. So to this point, what we focused on primarily what we generally call univariate statistics, right? I've got one IV and one DV, right? For our t-tests, right, I've got, if I'm looking at a paired sample t-test, I'm looking at sort of the relation of sort of a group or sort of a change over repeated assessments. If I've got an independent sample t-test, I'm looking at how's this group different than that group, right? So we've got one variable, one IV that's a grouping factor, and one outcome variable. Same thing when we got into ANOVA stuff, right? We have more groups, but we still have just one grouping variable and an outcome, right? We've got, like, say, class standing, freshman, sophomore, junior, senior, right? That's just one variable. It's 4 levels, it's just one variable. How's that related to GPA or drinking behavior or something along those lines, right? So all the stuff that we did last semester, with the exception of the factorial ANOVA, is going to be those univariate statistics, right? And these are good tools. But problematic, or things that are problematic with univariate statistics that start to limit us a little bit, they can be kind of inefficient, right? Let's say I wanted to look at the association between gender and college performance, okay? Well, what do I mean by college performance? There's lots of things that go into college performance, right? I've got how many courses I'm taking. Am I attending class? How many hours am I taking? What's my GPA? What's my major GPA? Like, how invested am I in my education? Do I like the courses that I'm taking? There's just so many different ways that we could go through and think about and conceptualize college performance. Now, if I'm just stuck in univariate statistic mode, I could go through and have my, however I decided to conceptualize gender, and I could look at sort of differences across groups, across each one of these things, but that could easily end up with, 5, 6 different models, all with sort of stuff that I got to go through. It starts to get pretty burdensome and cumbersome if we're just looking at things 2 at a time. Okay. It also limits the types of questions that we can ask, right? I can say, what's the relation between trauma severity and psychological distress, right? Do men and women differ on levels of PTSD? Is there an association between social support and PTSD? I mean, these are things from my area, and these are fine questions, but like we can only ask them so many times before it starts to get pretty boring. And like we've already established sort of that there are associations there, and I'm kind of over it, right? So again, what we've got is some limitations. Our univariate statistics are phenomenal tools, and often our more advanced statistics often end up sort of coming back to these, but on their own, they're pretty limited in a lot of different ways, okay? So our solution is going to be transitioning into multivariate formats, Okay. Now, all of a sudden, what we're going to do with multivariate statistics is we're starting to look at and model relations between sets of variables. Okay. So it's not just one IV, one DV. What we're going to do is we're starting to go through and sort of pull things together. Again, it's the same basic principles. We're just kind of layering things on top of that, right? That's what I think is really cool about this 2-semester sequence is we're never really introducing things that are completely new. It's just kind of building on stuff that we've already done, right? So we know what a t-test is. Now what happens if we start adding on attachments and sort of building it up, right? So with our multivariate statistics, what we can do is we can start looking at multiple predictors and multiple outcomes, okay? There are a few things in psychology that are determined by one thing. Usually behaviors that we're interested in have a whole bunch of stuff that are influencing it, right? With multivariate statistics, we can start to go through, put those things together to go through and say, hey, what are the influences on this, okay? Other thing that we can do that's statistically pretty cool is we can start to capitalize on sort of the interrelations of different types of different variable sets to maximize power, right? If I'm just looking at sort of the relation between or differences on one sort of DV, that's fine. But sometimes if I can start to cluster these together, I can capitalize on sort of how those things relate to one another and start to make for more powerful statistical tests, which is pretty cool, okay? I can also start to, and this is probably the most important one, is I can start to ask more interesting questions. I can start to put together things that probably are better represent sort of the behavior I'm actually interested in understanding than just saying, does this differ based on X? Is this thing related to that thing, right? So what we can do is we can start to ask more interesting questions that start to really give us a sense for what's going on with some of these phenomena, right? Thinking about what factors change the relationship between trauma and exposure and distress. Does anybody know what kind of question we're talking about there? Any guess? What question? What kind of question are we asking there with that first one?
Is that a moderation?
Yeah, it's a moderation, right? So here's a relation between X and Y. Are there third factors that go through and start to change the nature of that? Like, is X related to Y the same way for always and forever under all circumstances? Almost certainly not, right? What are the contextual factors that start to change that association, right? What are the boundaries of that association? Yeah, X is related to Y, but under what circumstances? Like, are there situations where X isn't related to Y, or X is related to Y more strongly, right? That starts to be kind of a more interesting sort of understanding of human behavior than just saying, is this variable related to that variable? Okay. Things like what factors account for the relation between trauma exposure and prolonged distress, like mechanisms of action. What types of things are we talking about there? What's that question? Any ideas?
Mediation.
Yeah, nice work, Kate. Yeah, it's a mediation question, right? We're looking at mechanisms. So we know that X and Y are related. Why? Like, what are the things that transfer that relation from X to Y? Now, all of a sudden, that starts to get into some conceptual models. I can see that this thing is related to that thing, but if I know why and can start to explain that process, that gives me a really good way to go through and start to modify behavior, sort of points for intervention, sort of understanding why people act the way they do. Really cool stuff. Okay. What are the unique contributions of various risk factors to the occurrence of PTSD? What type of analysis are we talking about there? Kind of correlation, but again, I think Haley, the thing here is the unique contributions. What if we go from just like what's the association to unique associations? What are we talking about there? Gabe, I see you mouthing. Do you mean to have your mute on?
I forgot I removed my face on the pen.
What's that?
I removed my face.
Right. I don't know. Do you have a guess on what type of analyses we might be looking at here with a unique relation?
This is like a regression or something?
Yeah, this is a regression, right? What I'm doing is I'm saying, okay, here's a number of different things, right? Here's a bunch of different factors I think might contribute to this outcome. Let's put them together and see what's the unique contributor, right? So again, we can start to ask, and so these are all regression-based questions, but even with regression-based questions, start to do stuff that's a lot cooler than just saying, hey, are these two things associated with one another, right? So if you like statistics and research, that's a pretty cool thing. All right. So lots of different models. How do we keep them all organized? Okay, this is where our GLM comes into play. Okay, generalized linear model. This is a broad model. It's the umbrella model. It captures a ton of probably nearly all of the types of analyses that you might just generate off the top of your head. Okay, this is like your common denominator for both our univariate and multivariate statistics. This is the internal combustion engine of inferential statistics, at least from a frequentist approach as we would use it. Okay, like this is the same thing, right? The engine in your lawnmower and the engine in your Ferrari are very different, but they work on basically the same principles, right? And that same principle is your GLM, okay? If you understand and sort of basically familiarize yourself with basic characteristics assumptions of your generalized linear model, it's going to help you organize your analysis. You're going to be able to say, okay, what are my inputs? What are my outputs? What's the level of measurement? If you answer those two questions, all of a sudden your options for analyses start to become pretty small and easy to choose from. Okay, so again, choosing your appropriate models, and then for anybody who wants to go on and sort of have a career that involves research and sort of maybe some statistical analyses, this is like the building blocks, right? This is like, if these are the basic things, if you have a good understanding of basic GLM types of stuff, regression, you're going to be in a good spot to then go through and start to add on new tools and things along those lines. Okay. So some basic assumptions of your general linear model. Okay. First thing with a general linear model is a basic linearity assumption. What we're assuming is that with any GLM type of analyses, we're assuming that pairs of variables hold a linear relation with one another. Okay. So again, with multivariate analyses, we've got lots of different variables, but what we're assuming with this model is that any two pairs of those variables hold. We can define that relation with a straight line. Okay. So again, any two variables in the model should be reasonably represented by a straight line. And if we violate that, what ends up happening is we start to miss possible associations, or the association that we model between X and Y is weaker than we would think, right? So if we go through and take a look, Mandy, what is, in this figure right here, what's the relation, at least in these data, between husband's age and partner's age?
Can you ask the question again?
Yeah. How would you describe, what's the relation between these two variables?
I would say that their ages are like arts. So like as the wives get like young younger, like their husband's age are generally like higher.
Yeah. So, yep, we've got a linear relation, right? Like his husband's age increases, wife's age increases, at least in the set that we've got here, right? Olivia, how is this a strong association based on the plot here?
It looks relatively clumped together, so I would say so. Yeah.
Yeah. I mean, in actual real data collection, this is a crazy tight association. Like this is really Haley. Can we describe this relation with a straight line?
Are you asking like it's? Sorry.
Oh.
Are you asking if it's like it's a positive correlation? So
Yep, it's positive.
What you're...
Can I use a straight line to describe this association between these two variables? Yeah. Really, really well, right? So this is a good example of something that would be like sort of very, very clearly meeting our linearity assumption. Okay. What about this one, Abby? How are these things related?
feel like we still might see kind of a loose pattern of like a negative correlation, but it would be a much weaker relationship.
Yep, exactly, right? We've got kind of as horsepower increases, drive ratio decrease. I don't know. This is just like sort of random graphs I pulled off of Google, right? But sort of what we've got here is as my X value increases, I see a reduction in my Y value. Not nearly as strong as that, right? But Lindsay, does a straight line reasonably account for sort of this association?
No.
Yeah. What type of shape do you think would better account for this?
Well, I guess if you were drawing a line through the middle, it would be straight, but it's not like closely.
Okay.
It's not close to that line.
Okay. So this is a good thing, right? When we're talking about linearity assumptions, right? The idea is that a line should give us close to the best shape to go through and approximate that the relation between those two variables. Doesn't mean that it follows a straight line. Doesn't mean that it's necessarily this. It's just, is there a better option for me to go through and model this? And here, probably not, right? I can go through and sort of draw a line down through. It doesn't do a great job, but I don't know if there's a better curve that's going to go through and get stuff. I mean, maybe kind of like a U-shaped kind of a thing, but I'm not confident in that, right? There's just not enough data points for me to sort of say like, oh yeah, that's the way to go with this. So here we would say, still meeting our linearity assumption, it's just not nearly as strong as an association as this. Okay. What about this one right here? Daniela, what's the association here between education and income, at least based on this graph?
So, like, the more educated you are, the more income you have.
Yep.
This isn't as strong as the husband age, wife age one, though.
Yeah. So it does look like there's some sort of positive relation between these two variables, right? Allison, is a straight line the best sort of shape to account for this association?
I would say it's more like exponential. Like,
Yeah,
it increases more as you get.
Yeah, as you sort of
income increases more as you have higher education.
Yeah. It looks like sort of the rate of change is not constant across this, maybe. Now, I don't know, right? But it looks like we have some exponential stuff. Is if I'm looking from 6th to 12th grade, and I just cut it off right there, yeah, that looks like a pretty good relation. But there's something that happens when you get into graduate work that looks like it starts to shift it kind of up the thing here. Now, Jalen, could I represent these data with a straight line?
I think it would be ugly.
Yeah, right. I mean, I don't even know if it would be ugly necessarily, but it might not capture everything, right? I could go through and draw a straight line right through here, and that's going to get most of it. But then I've got this stuff up here that the line's really kind of missing, right? And so this starts to get into what we're talking about when we violate that linearity assumption. We have to sort of pros and cons. There's no free lunch, right? I can represent these data with a straight line, and that straight line's probably going to be okay. It's pretty good, right? Now, if I'm looking at this, I might have a curvilinear function that does a better job of capturing it, right? Allison's saying maybe something that's exponential, a quadratic or something like that, that's kind of, it's not just a straight change, it's sort of maybe gone through. Now, the drawback to that is that adds complications to my model. That makes it less parsimonious. It makes it more complicated and harder to interpret, right? But if that's the nature of the association between those two, then there may be benefits to that. Or maybe the data that we're just seeing here just kind of has something weird going on that makes it look like it's exponential. I don't know, hard to tell, right? But if this is a true exponential association, but I model it in a line, does my line adequately represent the true relation between those two variables? What do you think, Johnny? No, right? What it's going to do is my line is going to say, yeah, it kind of fits, but my line is going to underestimate the actual relation between those two variables. It's going to say that education and income hold a weaker association than they actually do. It's just the real association is not perfectly represented by a straight line. So we're going to underrepresent sort of what the actual relation is between those two variables. Okay. People understand the linearity assumptions here and kind of what we're looking at with this. Okay. What about this? Johnny, what is this? Do I have a violation of linearity with these data?
I would say so.
Yeah. What shape do you think best describes these data?
I don't think a line would, and I don't think a U shape would either.
Is there an association between X and Y in these data? No.
Doesn't look like
No.
it.
So does a line do a great job of accounting for it? No. But does any other shape? No. Right? This is just true random data, right? And so here, our line isn't great, and our sort of regression coefficient is probably going to be 0, but there's not a different shape that better accounts for it, right? So this technically isn't a violation of linearity. It's just we have two random variables that don't hold an association with one another, right? So remember, anytime we're talking about violations of linearity, we're asking, is there a different shape that does a better job of accounting for this stuff? All right. So any questions about linearity? Okay. Other assumption, basic assumption from our generalized linear model is something we would call additivity. Okay. What we're assuming as I go through and add in predictors of whatever it is I'm trying to account for, my best, most efficient models say that I add my first predictor and it counts for this piece. And then I add a second piece and it counts for a different piece. And I add a third piece and it counts for a different piece, right? And if I've done this, my individual variables, my individual predictors start capturing different components of whatever it is I'm trying to predict in a way that goes through and makes for a really nice and efficient model, okay? So for example, let's say that I'm doing some marketing stuff and I'm interested in the extent to which people are satisfied with grocery stores in their area. Is anybody satisfied with the grocer availability in Laramie? Yeah, that's kind of thumbs down. It's pretty poor, actually. But if I wanted to put together a model where I was sort of like, are people happy with their options for buying sort of food, produce, and things like that? Maybe I might start thinking about, okay, like what are the things that contribute to satisfaction? Well, maybe I've got selection. Are there things for me to buy? Like, are there a reasonable number of things for me to choose from? Okay. And then I might say, okay, maybe prices, right? Prices aren't necessarily have to be related to selection. Prices can be independent of selection. Is everything marked up real high, or is it pretty cheap and affordable? What do I like there, right? Location, like where is it at? Can I get to it easy? Is it in a weird place? Things along those lines. Layout of the store. If I go into the store, can I find things? Is it kind of a mess? You know, do I get claustrophobic because I can't move around, or is it so big that I can't find anything? What's customer service look like? You know, are people helpful? Am I able to get in and out of the store? Things along those lines, right? So if I'm trying to put together a model that accounts for community satisfaction with their grocery option, their grocery store options, this could be a pretty efficient model, right? These different things add and capture different parts of sort of my overall satisfaction. These things are not necessarily highly correlated with one another. I've got a really nice additive model here. Okay, people seeing this? But let's say I go through and I want to go through and I create another model, and here what I want to do is I want to account for personal wealth. Okay, so I start thinking about, okay, what are the things that sort of start to contribute to personal wealth? Okay, so maybe in terms of predictors, I want to look at education. Okay, so people, higher levels of education, I'm betting that so they're going to have higher levels of personal wealth. And then family education probably too, right? Starts to go in and sort of contributes. Probably family wealth, right? I know that some of those things start to contribute to sort of generational wealth and things along those lines. Geographic location, right? Like where are people living, right? Like we're in sort of Southern California, or in rural Mississippi, right? There's probably going to be differences sort of going on there, right? Training opportunities. Do people have opportunities for internships and sort of training, sort of mentorship and things along those lines? Okay, and this is going to go through and be my thing that I'm going to use to predict personal wealth in my sample. Okay. What do we think about this model in terms of predicting our outcome? At least with respect to additivity. Do we like this?
Not as much.
Yeah, why not, Abby?
I feel like family wealth and family education are like pretty big indicators of education.
Mm-hmm. Yeah,
And
what
so I feel
else?
like they're not necessarily measuring like super distinct things.
Yeah, what else? Other people have sort of ideas on how maybe these aren't sort of this isn't going to be a super efficient model?
I feel like geographic.
What's that, Gabe? One more time?
I feel like geographic location to explain well. You have more involved.
Yeah, I'm not sure what you said. It sounds like it was right on, though, right? I'm having a hard time getting a sort of audio from you. But yeah, I mean, sort of basically the situation is all of these things are all kind of related to one another, right? Like if I get a group of people who come from a lot of family wealth, probably those people also have a higher level of education. The likelihood of me having a higher level of education is probably higher. Like sort of the opportunity to go through and have internships and sort of network with people and get plugged in with dad's company and things like that. Like these are all my predictors, they're fine conceptually, but they're all kind of stacked on sort of this underlying sense of family resources, right? Not 100%, but they're pretty related to one another, right? And so what I would say is this is a less efficient model, right? I don't know that my education adds anything to the prediction of wealth above and beyond my family education. Maybe it does, but it's probably not that much. It's not a completely distinct construct, right? Probably is family wealth related to geographic location? Yeah, we see throughout the U.S. that different sort of parts of the country have higher levels of wealth. It tends to cluster, right? And so what we've got here is what we're doing in this model is we're kind of measuring a lot of the same things with each one of our predictors, right? So we don't have a real nice, clean, parsimonious additive model here. What we're kind of doing is we're kind of measuring the same thing over and over again. We're just calling it different things and looking at it in different ways, right? So again, an important thing, and when we get into regression, we'll start to think about this now. For psychological constructs, like if I'm looking at extroversion and neuroticism and sort of psychopathology and shyness and anxiety and sort of these, it's all constructs that are related to one another, right? So we can't get away. We rarely have these nice, really truly additive models. But what we want to be mindful of is, are we including the same predictor in the model over and over again and just calling it different names? Because if that's what's happening, we're probably going to have problems with our model. Okay. Do people understand sort of this idea of additivity with this? Okay. Awesome. So what does our generalized linear model look like, right? Technically, something with lots of exponents and sort of subscripts and superscripts and things along those lines. So this can get pretty complicated, right? But if we want to get down to sort of kind of the very basic, sort of kind of the most pure representation, we might go through and start looking at just like a basic regression model, okay? So again, we got a lot of trauma variables just because that's what I had when I was putting together examples here. But if we say, what's the relation of depression to post-trauma symptoms in community survivors with PTSD? So we got 208 people, right? What we could do if we want to ask that question is we could just estimate a simple regression model, okay? Y hat here, this is our predicted value of Y. This isn't an actual value of Y. It's a model implied value of Y. Okay, really important to recognize. This isn't, Y hat might not correspond to any actual observation that's in our data, right? It's just saying based on the model, what do I predict Y to be? Okay, so Y hat, this is our expected value of Y or our predicted value of Y. A, this is our intercept. This is just telling us this is giving us our launch point, where we start from. B is our coefficient. This is our rate. This describes the association between X and Y. And X is just the value of our predictor. Okay. So if I go through and I run this model, and so I actually got a regression model that says my predicted value of Y, or my expected value of Y, is equal to 24.8 plus 1x. Okay. And this is just a basic, very basic, simple, but very nice and elegant representation of our general linear model. Okay. If I go through and I plot this out, this is what my data look like. Daniela, what kind of relationship what kind of relation do I have here between depression scores and PTSD scores?
A positive relationship?
Looks a positive relationship, yeah. Is it very strong?
No, it's pretty sparse.
Okay.
It's not as strong as the nice, pretty first example.
Well, yeah, but also I told you that that's not a realistic sort of stuff. This is actually, in terms of like data that you get, this is actually sort of looking like probably a pretty strong association between these, right? Again, this is pretty. It's not the straight line that we saw in the other, but that was kind of just some made up data here, right? But you're right, a positive relationship, clear sort of saying as depression scores increase, we can expect PTSD scores to increase in community survivors of trauma, right? And if we go through and we draw our regression line, this is kind of what that looks like, okay? So it's not perfect. We don't capture everything. We've got some stuff down here. We've got some stuff down here that we've missed. These are cases that we're not accounting for super well with our model, right? So here, this is the value that my Y hat for someone with a score of, we'll call it 46 on the BDI. I would expect their PTSD score to be here. This person's actual score is 0. So that's weird. I'm not sure what's going on. This model isn't doing a good job of accounting for that case. But for the data overall, this is the best fitting line that accounts for what's going on in terms of this association. Okay. So if we go through the other thing that's nice about this model, and again, like encouraging people, don't ignore your equations. Always look at your equations, because your equations and your formula tell you so much about what's actually going on in your data, right? So if I go through, based on my equation, what's the expected value of PTSD when my depression score is equal to 0? Jalen, do you have an idea?
Sorry, can you repeat that?
Yeah, what's my expected value of PTSD when my score for depression is 0? So if I have a score of 0 on depression, what do I expect my value of PTSD to be?
Is it the 24.8?
Yep, 24.8, right? Pretty easy, straightforward. All you do is you just go, if I go through and plug in 0 for X, well, then I'm left with 24.8. Like that's sort of my literal value there, okay? Jalen, one more time. What's the expected change in PTSD given a unit increase in depression?
1.
Yeah, right? And again, I just look at my coefficient here. My model is saying for every unit increase I see in a BDI score, based on these data, I'm expecting a corresponding unit increase in PTSD score, right? So what we've got is a lot of really, really excellent information and a lot of really specific information about what's happening here. Now, Johnny, does that mean for anybody I grab out of the universe, every time I see an increase in BDI, I'm going to see an increase in their depression score? No, right? This is just a guess. This is my best guess about overall, on the aggregate, how is this thing going to relate to this other thing, right? It's not perfect, and I'm going to have a lot of misses. But if I'm trying to predict this with a straight line, any other line that I predict is going to be a worse predictor, and so this is the way to go through and do sort of based on our GLM. Okay. Questions about this? Okay.
What?
Oh, yeah.
What did you say A was called?
That's
So
your
what is A in the
that's your intercept. Got it? Yeah. And that's your starting from. When everything and your intercept, always when we're doing regression stuff, The question is, what's the relation of X and, or my predictor with my outcome when everything is else held constant at 0, right? This is great because if I hold something constant to 0, what happens to everything else that I multiply things by? They go away, right? And so 0 is holds a very special place within the context of regression. We'll revisit this quite a bit as we work through stuff. Right. So my bivariate general linear model has 3 different forms that we can talk about in terms of bivariate analyses, right? If I have a continuous X value and a continuous outcome, talking about a Pearson correlation, okay? Again, if I'm sort of, I've got these data, how do I go through, what analysis do I use? Well, what are my inputs? What are my outputs? What's the level of measurement? If I answer those 2 questions, the rest is easy, right? What happens, though, if I have a dichotomous predictor and a continuous outcome? What forms can we use there? Couple of different things, right? We've got a t-test, right? And that's what we've used before. T-test is just a special sort of case of my generalized linear model. I've got a dichotomous predictor or a dichotomous input variable and a continuous outcome variable. We spent all last semester just running t-tests on that type of stuff, right? But what I could also run is a point biserial correlation, which is mathematically equivalent to my t-test and also mathematically equivalent to a Pearson correlation, okay? Same. I can do it, or I can run it however I want to. Mathematically, they're identical. We talk about them a little bit differently, but they're all just special different versions of the GLM. If I have a dichotomous input and a dichotomous output, now we're just talking about a chi-square test, right? Experimental folks, you end up doing a lot of, I know Psych and Law ends up doing sort of a lot of chi-square types of analyses and stuff like that if I've gotten grouping variables and looking at dependence there. But I can also, if I've got a 2x2 chi-square, I can also run that as a phi coefficient, which again is identical to a Pearson correlation, right? So again, sort of recognizing how our GLM sort of works and how this all works back and forth together is a really nice way to be able to go through and recognize. So I'm reading Olivia's paper, and Olivia is reporting something as the relation between a grouping variable, condition 1 and condition 2 with some outcome, and she reports it as a correlation. That's perfectly fine if Olivia wants to report it that way. Like, I can get mad and be like, you need to report a t-test. Like, no, she doesn't. Like, it's the exact same thing, right? I mean, the statistic is different. We talk about it as an association as opposed to a group difference, but mathematically they're equivalent tests, right? Because they're all different versions of the GLM. Questions? All right. So again, what we start to see when we transition from kind of the group-based stuff that we did in the first semester into a GLM type of framework, functionally they're identical. Mathematically they're identical, but how we talk about things starts to get a little bit different. What we do is we start talking about relations between variables as opposed to group level differences. And there's some reasons that this can be really kind of beneficial. It gives us more flexibility, right? If I'm talking about group level differences, let's say in ANOVA, I can say, okay, well, this is different than that, and this is different than that, this is different than that, which is a fine way to go through and talk about things. But what I could do instead is I could just say, hey, this categorical variable looks like it holds an association with this outcome, right? It's a much more flexible way to go through and think about things and starts to lend itself better to the types of analyses that we'll start to run with regression, multivariate analyses, and things along these lines, okay? So what we do then with that simple bivariate GLM is we can start to add multiple predictors of Y. We can start to sort of add things to the left hand of that equation, right? Where we're going through and we're saying we just don't want one predictor. I think there's actually a number of different factors that start to influence outcome, not just one, right? So let's go through and start adding in additional predictors. If I do that, then I start to get into a multivariate GLM, okay? So again, instead of just saying what's the relation between depression and PTSD, maybe what I want to know is what's the relation between depression, trait anxiety, and social support with PTSD, right? Now all of a sudden I'm starting to model in more factors that are probably going to do a better job of accounting for my outcome than just one thing alone, right? I can start to build a better model that probably better represents what's going out there in the actual universe, and that's a pretty cool thing. I can start to get more interesting and complex analyses with this, okay? Now, note that when we go from our bivariate associations, right, which is going to be our correlations and stuff like that, into our multivariate multiple regression framework, now all of a sudden these coefficients here, they start to change just a little bit, okay? With this, with only one predictor, if I go through and standardize this, what do I have? Anybody know? It's essentially a correlation. I ran it in a regression model, but it's essentially a correlation. It's the relation between x and y. There's nothing else going on in the model, right? So if I were to look at the standardized coefficient for this regression equation, it would just be equal to a correlation, right? Here, with my multiple regression, now all of a sudden what we have are these going to be what we call partial coefficients. We're going to spend a lot of time talking about partial coefficients. What these are looking at is capturing the unique association between depression and PTSD after we account for anxiety levels, after we account for social support. This is the unique association of social support with PTSD after I pull out stuff that's shared with depression, after I pull out stuff that's shared with anxiety, okay? So if I standardize these, my coefficients in my multiple regression aren't going to be equal to my correlations, okay? What these are going to do is they're going to be partial coefficients, and so we'll get into more about that and what that is. But if I've only got a bivariate regression where I've just got one predictor, one outcome, my standardized coefficient there is equal to my correlation because it's just the same thing going on there, okay? So again, really wanting people to be able to start to see how we can move back and forth between these different analyses and how they relate to one another to give us some flexibility in terms of interpretation approach and things like that. All right. So my simple multivariate GLM, if I got a continuous predictor, continuous outcomes, we're talking about regression models. Okay. If I have a discrete predictor, or multiple predictors that are categorical in a continuous outcome, here's where we get into our ANOVA models here. If I have a mixture of categorical and continuous X's and a continuous Y outcome, now we're getting that like ANCOVA types of models. If I have a continuous predictors and a categorical outcome, we have what we would call a discriminant function analyses. You don't have to worry about this. People don't do DFAs really all that much anymore because there are better ways to go through and do things. Basically a logistic regression, right? If I've got a mixture of categorical and continuous predictors and a categorical outcome, logistic regression is a really nice way to go through and start working with this, right? And then if I have a mixture of categorical and continuous predictors and some time-based outcome, we're talking about some survival analyses and things like that, right? So again, as I'm going through, you don't have to necessarily worry about this right now, but it's just a way to go through and see how we can start to organize what analyses that we might want to use simply based on what are the variables that I want to model, what are my inputs, what are my outputs, what's the level of measurement. We start figuring out, things start narrowing down pretty quickly with this. Questions? Okay. Oh, whoops, and then some time series stuff there. Okay. All right. So to this point, right, we're talking about our simple multivariate models. And we like that because we've got more predictors. We've got sort of more predictors of some outcome that we want, right? Problem is that a lot of the criticisms that we leveled against our bivariate analyses, we could also level against our simple multivariate models, okay? Sometimes these can be cumbersome and inefficient. What if I have multiple outcomes that I want to account for, and those are all kind of related, right? Our simple multivariate model still won't handle those, right? And again, starts to limit the types of associations that I can look at if I'm limited to one dependent variable, okay? Again, what if I have multiple outcome variables, right? Again, going back to our college performance example, we've got lots of different things that could constitute performance in college, right? Now, I could run all my predictors on each one of these things individually, but I'm still going to end up with lots of different models, right? So what we've got then is going to be our full multivariate generalized linear model, okay? With our full GLM, what we've got is we've got multiple predictors and multiple outcome variables, all right? This is way more complex, but all we're doing is we're just layering on the stuff that we did before. We just added in, we already had a bunch of predictors. Now we're just adding in a bunch of different outcome variables here, okay? The leap that we get with the multivariate stuff, with the full multivariate stuff, is what we also often need then with our regression model, right? Kate, if you run a regression model, a multivariate regression model, you're just going to have one regression equation that qualifies sort of how you've modeled that relation, right? If I get into a full multivariate analysis, what's likely to happen is in order to account for all the relation between all the predictors and all the outcomes, what I now need is multiple equations to go through and capture, get a unique solution for this, okay? So similar to thinking about, sort of go back to like middle school algebra, right? If I have x plus y equals 24, Lindsay, is that a solvable equation?
Sorry, can you say it one more time?
Yep. If I say, hey, Lindsay, x plus y equals 24, tell me what x is and tell me what y is that a solvable equation?
No.
No. Well, I mean, or it's infinitely solvable because you can give me sort of any two numbers. Well, not any two numbers, but sort of once you give me one number, you've got another number, but there's an infinite number of solutions there, right? What if I then say, okay, x plus y is 24, also 2x minus y is negative 6. Can now you get a unique solution for that? Now we can, right? And this is what's happening with our multivariate analyses. We're having to deal with multiple equations to go through and calculate and sort of account for the relations between all my x's and all my y's, okay? Now, when we get into these full multivariate models, what you'll hear people talk about is we're working with a number of different linear combinations of variables to capture what's going on with stuff. And depending on the types of analyses that you're looking at, you'll hear these called different things. Sometimes you'll hear them, so examples are characteristic roots, principal components, right? Depending on what analyses we're running, there are different names that people use for these, but essentially they're the same thing. It's the mathematical equations that we're using to describe the interrelations with these outcomes, okay? I'm not going to ask if people have questions because I'm sure you do, right? Good news is this full multivariate stuff gets at a level above what we're going to cover this semester. If we're looking at our full multivariate analyses, again, within our GLM, if I have continuous x's, a set of continuous x's, set of continuous y's, we're looking at canonical correlations. If I've got discrete categorical x's and a series of continuous outcomes, we're talking about MANOVAs, right? If I've got a mixture of continuous and discrete predictors and a series of continuous outcomes, talking about MANCOVA stuff. If we've got discrete outcomes, sort of categorical outcomes, and a continuous repeated observation, now we've got repeated measures, ANOVA, stuff like that. We'll spend some time with this. If my predictors are latent variables and my outcomes or my observed variables are y's, I'm talking about some factor analysis, stuff like that. If I got a whole mix of continuous and discriminant, or continuous and discrete x's and continuous and discrete y's, now we're talking about some structural equation modeling types of stuff, right? So again, identifying, so what are my inputs, what are my outputs, how many of these do I have, what's the level of measurement, again, very quickly starts to put you exactly where you need to be in thinking about, like, how do I go through and run these models. Okay. Questions about sort of this general linear model and how we're using this to go through and understand progression through different types of analyses and how things fit together. And at this point, I just broad strokes, right? If you know, hey, within the GLM, if I identify what my inputs are, what my outputs are, identify level of measurement, now all of a sudden I'm sort of on a good sort of track and understanding things and recognizing that sort of we have equivalent analyses within some of these things. I mean, that's kind of the main thing you need to take. I'm not going to have you derive characteristic roots. Does that sound? Or do we have an agreement there? Thumbs up. Okay. Okay. So where do we start with this? Right. We've got kind of the 1,000-foot overview about sort of what's going on. GLM. So how do we jump into the middle of this? Let's start with correlation. Okay. Correlation is nice. Everybody, I am certain, is familiar with correlation, or at least has had some exposure to correlation. Hopefully, most of this stuff is a lot of review. Okay, so when we're thinking about a correlation, we're talking about the measure of an association between a random variable x and a random variable y. Okay, can someone tell me what a random variable is? What does it mean if I have a random variable? What do you think, Johnny?
I can just think of like a bunch of examples, but
shoot,
I guess.
You give me a bunch of random variables.
Well, like it would be something if you just hold something kind of out of thin air, like is MPG related to water consumption?
Sure, right. Yep. Random variables are going to be anything that I go. Oh, where did Mandy go?
I'm here.
Oh.
I raised my hand. I think that's why I made this.
Oh yeah, what's up?
I thought of an example.
Oh yeah.
Like ice cream causes like murders or something. Like in the summertime, just like super random. You think they might be correlated.
Okay, those can be random things that are correlated. Yeah, I think those all good examples. Here, a random variable is anything that I'm just going through and I'm sampling, right? I'm just going through. A random variable is anything that I go out into the universe and I just get values. Okay, I don't determine what those values are. I'm just going through and grabbing stuff. That's going to be my random variable. And when we're looking at a correlation, I've got random variable x, random variable y. I've just got two different constructs that I've gone through and just sampled. This is technically sort of the heart and soul of correlation, okay? And what we're using is a bivariate normal model. And what we're doing is we're assuming that we've sampled both my x variable and my y variable with error, okay? I'm allowing myself and saying, hey, I've measured x and I've measured y, but within my bivariate normal model, what I'm assuming is that I've gotten some error in both my x and both my y, okay? So this is what we're looking at with a correlation. Regression is a little bit different, okay? Technically, within regression, my statistical model with regression, I'm technically assuming a fixed variable x that I use to predict values of observed values of my random variable y, okay? So here, with a fixed variable is different is because I get to choose what the values are, right? What I'm going to do is I'm going to say I'm looking at people. I'm looking at housing price and life satisfaction, let's say, right? So I go and I don't sample homeowners. Well, I sample homeowners, but what I do is I go through and I got a list of people, the value of people's homes, okay? And what I do is I go through and I say, all right, I want 10 people with a home of this value. I want 10 people with a home of this value. I have 10 people with a home of this value, 10 people with a home of this value, and specifically select people for a specific value on my predictor, which is home prices, right? And then what I got, after I get all those people with each level, then I go through and I ask them to tell me sort of life satisfaction. Life satisfaction, that's random. I'm not determining their answers there. They're just sort of telling me their level of life satisfaction. But the fixed variable is something that I'm specifically choosing. Okay, it's me going into the jar of jelly beans and specifically picking out 20 blues, 20 greens, 20 purples, 20 reds, 20 blacks. It's a fixed variable model. Okay, so what I'm assuming here is that I'm measuring X without error, and I'm looking at how that variable predicts my random variable Y, which I'm assuming is going to have some error in it. Okay, so this is at a statistical level the difference between correlation and regression. Correlation, the assumptions are a little bit different. I'm assuming a random variable X, random variable Y, and I'm assuming a bivariate normal model. Okay, for regression, I don't have as many assumptions because I'm assuming that that my predictors are fixed predictors that I've measured without error. Okay. Now, do we ever actually do this in applied settings? What do we think? Allison, do we ever do this in applied settings?
Yes.
Maybe. I guess I can't rule out, I can't say it's a universal no. Typically not, right? Because we're typically going through and we're our predictors that we're getting in regression they're typically random variables, right? Because we're just, hey, who's coming into my study? Whatever levels of your predictors are the levels that you come in. I'm not specifically pulling samples for that, right? But regression still works. We just have to change some of the assumptions is what we're going to spend a lot of time just sort of looking for with stuff. But so just thinking about sort of statistically, there are some differences in sort of correlation and regression, even though we use these kind of interchangeably a little bit. Yeah, Mesa.
Aren't the specific populations we choose to use a fixed variable? Like, specifically, if I want to work with people who have ADHD, isn't that a fixed variable?
Well, it kind of depends, right? If your predictor is ADHD or not, and you sample people with ADHD and people without ADHD, and that's your only predictor, then you could treat that as a fixed variable, right?
Okay.
But generally what we're doing is we might have some stuff like that, right? But then we also have things like maybe you want to look at like history of childhood stuff, right? Or achievement or discipline referrals or something like that. I can choose my ADHD and my non-ADHD groups, but now all of a sudden all that other stuff they're random variables too because I didn't select for those, right? So almost always with the types of behavioral statistics that we do, we're almost always using random variables. But again, that's fine so long as certain things meet, and if they do, then our estimates are fine. But from a classic theoretical standpoint, so we've got different assumptions for correlation and regression. But great question, yeah. Okay. So,
Josh.
Yeah.
Sorry, I had another
Yeah.
question. I think I'm still a little bit confused about what a random variable is. Could you explain that a little bit more?
Yeah. So random variable is actually easy. Random variable is basically any variable, Lindsay, that you can probably think up in your head is probably a random variable, right? If you were to go through and just from our screening sample, let's say you have an eating disorder measure in there, that's a random variable, right? Like you're not telling people who can be in the study based on their level of eating disorder. Everybody's just reporting sort of their levels to you. And so that's like you get what you get. Like that's a random variable. A fixed variable starts to get into if, let's say, Gabe's doing a study where he's determining who is in what condition, and condition is his predictor. Now that's a fixed variable because Joe and Jane Schmo just didn't come in and get to tell Gabe what condition they wanted to be in. Gabe's like, nope, I'm getting sort of this many people in this condition, this many people in this condition, this many people in this condition. These are all the values of condition that exist in the world. I've sampled them all equally. this is my fixed variable. Okay. Random variables are the types of things that we do when we just like have whoever come in and do, and they just give us whatever characteristics they've got. Those are the random variables. Does that help clarify that?
Yeah, that does.
Okay.
If you're doing like a secondary data analysis and you're like looking at individual groups that like are initially random, could they then become fixed, or are they, if you're not selecting people based on a group?
Yeah, I mean, if you're selecting people for individual scores and having all those scores be representative of all the scores that there could be of interest on that thing, then you can start to model that and treat that as a fixed variable because you've chosen those people for that thing. But now if you go through and you start adding other things in, now all of a sudden now you've got more random variables in addition to a fixed variable, and then that screws stuff up again too. So you got to be careful, but that's kind of when you get into multi-level modeling, you hear a lot about it, talk about fixed effects and random effects and things like that. That kind of gets into some of this stuff as well. It gets pretty heady, sort of layers on layers on layers, but so this is the basic concept.
Okay.
Does that help?
Thank you. That helps.
Yeah. Okay. Other people sort of comfortable with this? Okay. So, yeah, what's up, Johnny?
I just had a quick question. So you said most of the time when we do like a regression, we don't have like a fixed variable. We're using like the random variable. Mm-hmm. Does that change any of our assumptions?
Yeah. And we'll spend a whole class period talking about the impacts of that. And so this is why we have to go through and screen our data. Technically for regression, we have no assumptions about our the sampling of our predictors if they're fixed variables, right? Because if I go through and if I intentionally select an equal number of cases of all relevant values of my predictor, what does that distribution look like? It's flat, right? Because everybody there's equal representation across the whole thing, right? Certainly not have a random distribution to that, right? But because we don't do that, now all of a sudden we have to have some distributional assumptions and things, and that's where we start to get into doing some of the screenings to make sure that our estimates aren't going to be all off base, that we can still have confidence in our inferences and things like that. Yeah, but again, we'll spend at least a class period just talking about all that stuff.
Okay.
Yeah.
Thank you.
Yeah. Okay. Properties of correlations. Correlations, easy peasy. Bounded by -1 and 1, right? Really, really efficient, a lot of information packed in there. The value of the correlation tells us the magnitude of the association. As we get closer to 1, closer to -1, tells us we have a stronger association. As we get closer and closer to 0, tells us we have a weaker association. Okay. Inferences regarding the direction, that's going to tell us the sign is going to tell us that. Sign is going to tell us, do we have a positive relationship or do we have a negative relationship, right? Positive relationship says as X increases, Y increases. Negative, as X increases, Y decreases. Now the sign can be kind of arbitrary, right? Like, is my sort of outcome coded towards functioning or impairment, right? Just the way we measure things, that sort of the direction can sometimes be arbitrary, but always, anytime when we get into this, never just tell me there's an association between X and Y. Because if you just tell me there's an association between X and Y, I don't know what direction that is. That could either be something that's consistent with what I'm expecting or not, right? So always make sure that you're very clear in your interpretations which direction that's going in, okay? And for any of you that are just really like, what you want to do with the rest of your evening is just play with correlations, and I understand the urge if it's there. Got this guess the correlation, this little link down here in the bottom of your slide. Pretty fantastic video game, like sort of right there with like Xbox level, where you get to guess the correlation, and you get lives if you get sort of really close, and you lose them if you don't, right? Again, there will be sort of extra special consideration and recognition, high praise for whoever comes away this semester with the highest score on Guess the Correlation. Like, this is an easy way to eat up like 4 hours of your day if you're not paying attention. So jump on there when you've got some free time. It's Jalen, you look skeptical. I'm going to turn you into a true believer with Guess the Correlation. You don't scowl at guess the correlation. Right? It really is fun. All right. Some quick refresh on a couple of different concepts as we to finish up here. Want to talk a little bit about variability. Remember that variability is just the degree to which scores spread out or clustered close together. Okay. If all the scores in my set are the same, then it has no variability, right? If there's lots of variability, then things are going to be all spread out. Okay. So variability starts to be an incredibly important concept particularly when we get into some regression stuff. We've got a lot of different measures of variability, different indices of variability, but they all just describe distribution in terms of distance, right? How we can think about sort of our different measures of variability is telling us how much distance to expect between two individual or randomly selected points in a distribution, right? If I've got a lot of variability, it suggests that if I select two random points out of there, that they're probably on average going to be pretty far away from one another. If I have very little variability in my data set, it says if I grab two randomly selected scores, they're probably going to be pretty close together. They don't have to be, but they're probably going to be pretty close together. Okay. And from a statistical standpoint, we can think about variability as telling us how well an individual score represents the full distribution, right? If I've got very little variability in my data, Danielle, and I grab a random person out of there and I say, hey, Danielle, how well does this person represent sort of the entire group? If there's not that much variability, what are you going to say?
Probably pretty good. Then.
Probably pretty good, right? If everybody's kind of about the same and I just grab a rando out of there, they're probably going to do a reasonable job of representing people, right? But if there's a lot of variability, right, and I say, hey, here's one score that represents the full distribution, you're going to have a different answer, right? You're like, maybe, I don't know. That score might represent the best, like the middle of the distribution, but there's so much variability. People are all over the place, right? Like, I don't know. It's maybe the best we can do, but it's not going to be really good. And so if I say this is the value for everybody, I'm going to have a lot of error in that data, correct? Yeah. Okay. So it starts to become important for our inferential statistics here. Okay. Now we talked about variability. If we talk about variance, that's a specific statistic. Okay. Variance, again, is our second population moment, defined as the average squared distance from the mean. Okay. If I take that variance and I take the square root of that, that gives me my standard deviation, okay? And remember, we can loosely interpret standard deviation as, on average, the difference of any randomly selected score from the mean. Not precise, because we play around with the denominator a little bit, but generally, about if I had to sort of randomly select a score from a distribution, and you say, hey, how far is this score from the mean? My best guess is going to be whatever the standard deviation is, because that's going to be like, on average, how far it is away. I'm probably not going to be right, but any other guess I come up with is going to be more wrong than anything else that I could guess, right? So again, remember when we're calculating variance, what we're going to do is we're going to have our values. We're going to calculate a deviation score, and that's just my observed score minus the mean. Then I'm going to square each one of those, right? Why do we square these? Haley, do you remember why we square these up first?
Because it does standardizing.
Yeah, so it starts to play into standardizing. What I'm going to do is I'm going to sum up those squared deviations. What would happen if I just summed up the deviation scores?
It wouldn't be okay, because there's like pooled variance. It has to do with like your pooled variance and like standard deviation. So it wouldn't be representative of the population. I feel like
this is a purely mathematical question. What happens if I add up all the deviation scores? This column.
Then you just get the sum.
I get a sum of 0.
Squares.
Yeah.
Zero. Yeah.
Zero.
Sorry.
Yeah. No. That's fine. Yeah, no, by definition, if I just add up my deviation scores, I have to get 0. It's going to be, that's the only score that I'm going to get, right? But if I go through and square those deviation scores and sum those up, now that gives me my sum of squares. That's my sum of my squared deviation scores. And now what I can do with that is I can divide that sum of squares by my degrees of freedom, n-1, and that's going to give me my variance, right? If I take the square root of the variance, that's going to give me my standard deviation, computational formulas, and things along those lines, right? So remember, in terms of variability, this is just sort of, we're talking about variability, we're just talking about how spread out or close together scores are, right? But if I want to talk about specific metrics, I can talk about sum of squares, I can talk about variance, I can talk about standard deviation. They're all measuring the same thing. It's just some are a little bit more interpretable numbers than others, but they're all representing the same concept. Okay, it's basically we're saying the same words, they're just in different languages, right? And some languages we understand a little bit better, and some languages we don't. Doesn't mean that those ones that we don't aren't useful. It's just sort of different ways of representing this. So what we've got is sort of using this as a way to sort of introduce this idea of covariance. Okay, covariance is a new statistic. It's going to tell us the degree to which two variables relate to one another. As we see variability in X, what kind of variability do we see in Y? Okay, and we calculate covariance as the sum of the deviation of X from the mean of X times the deviation of Y from the mean of Y, all over n-1. Okay, so if I've got some data, okay, we're going back to our depression and our PTSD scores. Here's the mean of depression. Here's the mean of my PTSD score. Okay, if I start to in my data, I see that large X's tend to be paired with large Y values. The sum of these products are going to be consistently large and positive. If I take this score right here and I subtract it from the mean of Y, that's going to give me a large positive score. And if I subtract it from the mean of X, it's going to give me a large positive score. And if I multiply large positive scores by large positive scores, I'm getting a large positive score. Same thing if my really small x's are paired with my really small y's. Now I've got a small x, subtract that from the mean, I'm going to get a negative value. Subtract that from the mean of y, I'm going to get a negative value. Now I'm multiplying large negative numbers by large negative numbers. It's going to give me a large positive number. Again, what's going to happen is I'm going to get a sort of positive covariance here. Okay. Now, if I have large x values paired with small y values, what I'm going to get is the same thing, except now the product of my deviation scores are going to be large and negative. Okay. Now we're not seeing this in this graph, but let's say I had a bunch of scores up here, right? Now I've got, or let's say down here, now I've got large x's, right, paired with small y's. So I take a large deviation score that's positive, multiplied by a large deviation score that's negative. If I do that a whole bunch, I'm getting a large negative covariance, right? It's going to say as x increases, y decreases. Okay. However, if I have scores where x are unrelated to y, sometimes I'm going to have large x values that are paired with large y values. Sometimes I'm going to have large x values that are paired with small y values. What's going to happen is the sum of those, the product of those deviations are all going to cancel themselves out, and I'm going to get a covariance that's somewhere next to 0, right? If this whole plot is just kind of a big cloud, there's no rhyme or reason to where x is related to y is, and so what's going to happen is I'm going to get a covariance that's very close to 0. Okay. So this is just going to go through mathematically, sort of understanding what covariance is and how it's calculated. Okay. But again, it's just a product of deviation scores. Okay. Statistics loves deviation scores. We're real into it. Right. Computational formula for covariance. This is if you just sort of don't want to sort of slug through. This is a definitional formula. This is by computation. Mathematically equivalent. They'll get you the same spot. Okay. So this gets us all to our Pearson product correlation. Okay. My absolute value of my covariance. So the value that I get for this is going to be a direct function of my standard deviation of x and my standard deviation of y. Covariance by itself doesn't mean anything. Covariance is like variance. If I say, hey, Mandy, I got a covariance of 54. Is that good or bad? You're like, who the hell knows? I don't know. It doesn't mean anything to me because it's just a raw metric, right? But if I go through and I take that covariance and I divide it by the product of the standard deviation of x and the standard deviation of y, what I do is I standardize that coefficient and it gives me a correlation coefficient. Now all of a sudden I've got a coefficient that's bounded by 0 and 1, or negative 1 and 1. I've taken that covariance. It's sort of like taking that covariance. If covariance is similar to like a sum of square, your Pearson correlation is kind of like a standard deviation. Standard deviation, I can tell you what that means. Sum of squares, I can't really. They're basically the same metric. They're getting at the same thing. It's just one's more interpretable than the other. Same thing with covariance and your Pearson correlation. Okay? So when you're thinking about this and you see covariance, you should be thinking about like a sum of squares type of thing, right? Same thing. We can take that, turn that into something that's standardized and interpretable. Okay? Last thing that we'll finish up with here is just recognizing that our Pearson correlation is not an unbiased estimate of the population parameter. Okay, even if two variables, the association in the population is exactly 0, is my correlation going to turn to be exactly 0? No, it's always going to be something. It's going to be incrementally bigger or smaller than 0. And so what we have is a biased estimate that starts to become problematic, particularly with small samples. What we'll see, and we've talked about this before, is we can take our Pearson correlation and run it through a small sample adjustment. What this does is it just creates a penalty for small sample size, right? As that sample size increases, the penalty decreases until we get asymptotically equivalent to R. But just recognizing that, similar to a lot of our different statistics, these are not unbiased statistics. So if you see a correlation with a sample of 20 or 30, you should probably know that that coefficient is probably going to be bigger than it ought to be, right? And so what we can do is we can get an adjusted correlation for small samples that probably brings that back in line with something that's a better estimate of the population value. Okay. All right, cool. We'll finish up there. I'll get through the rest of the slides in a video, so to post that up just so we're up to speed with stuff. You can go through, watch that, and then come talk to me if you have questions, or we can catch it in class next time we meet with stuff, okay? I know you got to get to the job talk. I want to give you time to travel there, so to do your stuff. So we'll cut it loose. Shoot me an email if you got questions. So good to see you all, and we'll follow up with things next week. All right. See you, everybody.